This is what we did last time. Any questions on this?
Sir, temperature control from
Compressor
temperature
का
control. Temperature control of heat exchanger.
this cooler,
No sir, heat exchanger.
which heat exchanger यार? एक तो ये कूलर है.
No sir. Yes.
अच्छा ये furnace.
Yeah, furnace.
हाँ बोलो.
That also can be controlled by the direct adjustment of the temperature controller and
Yeah, it can
flow
be done.
control.
Yeah, it can be done. So, but we didn't do it. Why did we not do it?
Due to legacy.
No, it's not due to legacy. It's because when you are trying to jack up throughput,
Yes.
furnace becomes active. Furnace duty becomes active.
Yes.
If you are using it for control, then to control that temperature, you will need some margin always, right? So you cannot take the furnace duty to 100%. You will have to operate on average at say 90% furnace duty, so that 10% margin is there to keep the temperature in control. Yes or no? हाँ बोल रहे हो नहीं बोल रहे हो क्या बोल रहे हो? हाँ हाँ. Okay, I repeat it again. Suppose I am using a variable to control something. Suppose, so let's say I am using Q furnace to control temperature reactor in. Okay, reactor in temperature is being maintained by adjusting Q furnace. Okay, let's say that's what I am doing. What happens to Q furnace? Temperature will be held constant, nearly constant, and Q furnace will go all over the place. Yes or no? Yeah, but this Q furnace should not exceed 100% max capacity, because if it exceeds 100%, then I lose temperature control of the reactor inlet. That is not acceptable. Okay, that being the case, if this is my 100% limit, my average operation will have to be below that 100% limit. My average operation is maybe 90%, maybe 95%, but definitely not 100%. So let us say this average operation is at 90%. What is this?
Margin.
Lost production. If I want to maximize production, and furnace is the constraint that limits production, furnace duty, then if I am using furnace duty to control something, so that whatever I am controlling remains controlled, I need this back off. Yeah, yes or no? That is why, because furnace duty becomes a constraint that will be active at maximum production, I am not using it to control anything, so that this throughput manipulator can be taken to 100% and left there. That means furnace duty valve is fully open. Okay, but I need to control the temperature of the reactor. Yeah, how do I do it? By adjusting the flow to the reactor. That's what is being done by this temperature controller. Yes or no? This is the reason why it was done. If furnace duty was not becoming an active constraint, then I would have done it the conventional way, temperature being controlled by adjusting the fuel to the furnace, by adjusting the furnace duty. But because furnace duty is becoming an active constraint, that is why I am doing it the other way. Yes or no?
Yes.
Huh? Okay. Any other questions? Why am I controlling the temperature in the why is it important to control the temperature in the purge column? This guy. First of all, temperature must be controlled. Why? Now I am asking questions. Since you are not asking questions, I will ask questions. Why is it important to control a stripping tray temperature inside the purge column? Forget what I used to control it with, but why is it important to control it?
So that C4 does not, NC4 does not leak down the bottom.
Yeah, so that I do not lose precious NC4 down the purge stream. That's why. So now the question is, so okay, it's very clear to me that I need to control a stripping tray temperature to ensure too much NC4 doesn't leak down the bottoms, because loss in NC4 leads to loss in production. Yeah, okay. Now the question is, what do I control it with? Yeah. If I control it with the conventional way like this, if I do it this way, what's the problem? The problem is boil up hits maximum constraint. Yeah, then I lose control of that. The moment boil up hits maximum, it will not be in my hands how much is leaking down. Whatever is leaking down is leaking down. It's not in your hands. Yeah, I don't want that, because I know from my analysis that boil up does become active. Boil up does hit the max constraint. Yes or no? So what do? Okay, I don't do it this way, I do it that way by adjusting the feed. Yeah. When it is not active, when the boil up is not active in the purge column, it can be used to control something. What is that something that I control? The way the control structure is drawn, I am controlling the amount of impurity C5 going in the distillate by adjusting the boil up. Yeah. When the boil up hits maximum, that impurity level will float. I lose control of it. Yes or no?
Again repeat, sir.
Again repeat, okay. Case is very simple. If I am using something to control something, if I am using a manipulated variable to control a controlled variable, okay. When that manipulated variable saturates, it reaches its limit, then the control of that CV is lost. Yes or no? If MV saturates, CV is not controlled anymore, it floats until MV becomes unsaturated again. Yes or no? That's very clear. So when a degree of freedom is lost, when a degree of freedom saturates or a constraint becomes active, control of something must be given up. Yes or no? If I was doing it this way, boil up is controlling stripping tray temperature. When boil up becomes maximum, NC4 leaking down the bottoms becomes floating. I lose control of it. That is not acceptable to me, because it has an economic penalty associated with it. On the other hand, when I am using the same boil up to control the C5 leaking up the bottoms, which is inside the plant, you see how much C5 is circulating round and round in the plant. When boil up becomes when boil up saturates, I lose control of that. That is less painful economically than allowing more C4 to leak down the bottoms and losing it forever. Do you see what I am saying? These decisions I have to make. What is more important? What is going to get saturated? If it is going to get saturated, when it is unsaturated, what should I use it to control, so that even if I lose it when it becomes saturated, it doesn't hit me much? Yeah. So how much is circulating around? Even if that floats, that doesn't bother you much, versus if the amount of NC4 leaking down the bottoms is too much. Yeah. So therefore, I need to control a stripping tray temperature. That's clear to me. How to control it? I don't do it this way, because boil up becomes saturated. I do it the other way. Yeah. When it is not saturated, the boil up, what does it control? It controls the C5 recirculating around. Yeah. That's it. These decisions have to be thought through. They are coming from what becomes active, what doesn't become active. Important variables that must always be controlled. What's the rule? What is the basic rule that comes out of it? Important variables that must always be controlled. The manipulated variable that you are using for them should be such that they don't become active. Yeah. Because should they become active, then what? Then you have lost control of that important variable, that quote unquote economically important variable. To the extent possible, I would like to make sure that that doesn't happen. right? Similarly, for example, there is a safety. Let's say you don't want the oxygen concentration inside a reactor to exceed a certain limit, because then the fuel, then the concentration is goes between the flammability limits. I must always use a variable that is what? That never gets saturated, because I can not afford that oxygen concentration to not be controlled. It must always be controlled. Yeah? Yes or no? Okay. So now let's go back to, I don't know which, so what are we saying? We are basically saying, one, how do you get tight control? Tight control will happen if the MV is close to the CV. Yeah? Yes or no? If the manipulated variable is close to the variable to be controlled, then the dynamics would be fast. If the dynamics is fast, I make a change in the manipulated variable, quickly the output variable, the controlled variable responds. I can close the loop and tune it nice, and what I will get is really tight control of the CV. So the first rule is MV should be close to the CV. That's the first rule. Yeah. Why should that be? For tight control. Yeah. What's the next rule? Next rule is avoid pairing MVs that avoid pairing with MVs that become active. Right? If you keep this in mind, structuring will happen automatically. Yes or no? Huh? Now we go back to, I don't know which day did we write, did I write that 9-step procedure? Do you have the date there?
16th August.
16th August, okay. Here is the 6, no, I think it's the next day. Yeah, it's just that in here it is written in one shot. Step 5. Step 5 and step 4. I bring your attention, well, maybe it should be in a different. Fix production manipulator, throughput manipulator. What is a good choice for a throughput manipulator? I am saying a manipulated variable that becomes saturated should not be used for control.
The one that becomes active first.
Active first or last?
First.
Last. To the extent possible, last.
So like in the last example, the furnace duty became active first.
Yes, I agree, and the penalty that you have there is that your throughput manipulator has to be shifted. Okay, this needs further discussion, doesn't matter. All I am trying to say is we will discuss it further. Fixed production rate manipulator. You see, you have constraints, manipulated variables that will become active. If you consider the rules that I just gave you, you would not be using those MVs for anything, or you would be using them to control things that can be given up. It's okay to control them, but even if they float, it's okay, right? Things that are not critical. Okay. Now what I am trying to say is, one of those active constraints that become active can be used for throughput manipulation. Whether it's the first constraint or the last constraint doesn't, that's further a level of detail. but one of those constraints that is going to become active can be used as a TPM. Yes or no? Yes or no? Yeah? Okay. So that's a possibility that you should consider. Okay? Okay. Step 5 says, so I would just like to say here that consider using one of the active MVs as TPM. Yes or no? That saves me a degree of freedom. Why am I doing it? Because that saves me a degree of freedom. This should not be touched. Well, I can touch it to manipulate throughput, because anyway I am going to be using something to manipulate the throughput. Yeah. So an MV that will become saturated, that's a good candidate. The best candidate would be what? The constraint that is the last one to become active. See, first I started jacking up the throughput. First this column got flooded, then this got flooded, then the furnace duty got maxed out. Okay, if the order is this, then I am better off using furnace duty as my throughput manipulator, and then my throughput manipulator is the same for the whole operating space, from low throughput to intermediate throughput to high throughput to maximum throughput. Yes or no? It is also possible that you may use a constraint that becomes active earlier and is not the last one. In that case, your throughput manipulator will switch. Once this becomes active, you still need to manipulate your throughput. What do? You go to the next constraint that is going to become active. Start jacking that up, and then your throughput will increase. Maybe that gets seen here. How do you go to a different file? File, open. Yeah. So if you look at this, what we did here, this is the throughput manipulator. I keep jacking it up. Then what happened? This became saturated. This was the first constraint to become saturated. Okay. Then what? Then my throughput manipulator shifted to basically this chap. What I would say is reduce the composition set point so that there is less C5 circulating around, and so the flow rate of this recycle stream or the distillate from this column will go down. Then the temperature here will go down, right, and I can suck in more. Yes or no? Alright, we discussed this, I don't know, in maybe some, I think we discussed this in detail. Yeah, basically what I am trying to do is minimize the C5 that's circulating around so that I can suck in more. What is circulating around in this loop is essentially NC4, IC4 and C5. IC4 leaks down the bottom of the deisobutanizer, C5 leaks up the top of the purge column. Now I am saying, okay, minimize this. So what I do, I start reducing the set point of the composition. As I am reducing the set point of the composition, the boil up will have to go up. Right, as boil up goes up, it will become saturated. Boil up will reach its limit. Once it reaches its limit, well, that's it. Jack up the production further, then I will go here. Minimize the amount of IC4 leaking down the bottoms. Right? Keep on increasing it, keep on decreasing it, and then what will happen is the boil up will keep on going up until it hits its max limit. And once it hits its max limit, that's it. So here I have had to shift my throughput manipulator from the first active constraint to the next constraint to become active to the next constraint to become active. There is this level of complexity that is there.
So why don't we choose the TPM as the last constraint to become active here?
And does it use?
Okay, you want to do that? Let's do it. Let's try and it can be done, but you will have to think. Well, okay, I have not done it before, but let's try doing it. So you are saying let's use this. This is the last constraint to become active. Let this be the TPM. That's what you are saying, right? Okay. Everything else goes. इसमें बहुत पंगे होंगे. Let's see what those pangas are. Okay. Okay. Furnace duty is something that will become active, right? So I flow control it, it's going to become active. Then what? Because I know it's going to become active, I say I am going to control the temperature using something which doesn't become active. Yeah? Okay. I need to control the amount of IC4 leaking down the bottoms of the de-isobutanizer. How do I do it? Since you are using this as TPM, boil up as TPM, the only option is to do this. Yes or no? Yeah. Then I need to control the amount of impurity NC4 up the top in the product. The only way to do that is by the way, this may be actually a composition controller, because de-isobutanizer, see, temperature is not a good measurement because the components are very close boiling. Okay, so basically what I am saying is this is composition control. Which
what about the lag associated with using the composition controller? Because usually the time is 6 to 8 hours. So
yeah, so there is a lag associated, so it's not going to be tight. Yeah, but it really doesn't matter because what's going down is okay. This goes into distillation. So if you can't use a temperature, what you generally use is a delta T, difference between two tray temperatures. Okay. So maybe what I can say is what you do is something like this. Why does that happen? Maybe we'll discuss it later. But delta T controller, and you can always have a composition measurement that adjusts this delta T set point. Okay. Now it will not be too slow. This can be done. So similarly, when I am saying composition control here, this could also be a delta T controller, and once a shift composition measurements coming from the lab is being used to adjust that delta T set point. Okay. I think that takes care of that. What else? I need to control the amount of NC. See, that's the problem here. Okay. I need to control the amount of NC5 that's leaking down the bottoms, or rather NC4. NC4 leaking down the bottoms. If I use the boil up, what happens?
It will hit max and we won't be able to control.
Huh?
It will hit max and we won't be able to control the amount of heat.
It will hit max, and so okay, so then you see, but I also need to control this level. The only way I can control this level is this. So I'll have to do it this way. Yeah. Once I'm having to do it this way, then basically temperature control has to be this way. Level control has to be this way. Yes or no? Yes or no? फंस गए यार, फंस गए कि नहीं? क्यों फंस गए? बिकॉज नाउ when this boil-up becomes saturated in the purge column, whatever NC4 is lost, I am helpless. It's just going to get lost. You see what I am saying? Can I devise a control structure that, how the hell do we do that then? Yeah, I can do it. And how do I manage this? इसका क्या करेंगे बताओ? What should I set the furnace duty to? See this furnace duty? Yeah, this is going to be problematic. I mean, the more I think about it, the more the previous one seems much more reasonable. What do I do with the furnace duty? क्या करें इसको? Okay, maybe I can do it this way then. Temperature control. Okay, in which case level control here will go this way. Then of course composition control is the conventional thing. Now what is happening is you will have to have some back off in your furnace duty. Yeah. So what's happening is you are having a back off in the furnace duty, you are also getting a back off in your purge column boil up, because it is being used to control a temperature. Yes or no? Just look at this structure. When this approaches maximum, you are going to start losing too much NC4 down the bottoms. You don't want that. So you'll always operate at a throughput where this valve is 90% open or whatever. You are only 90%. You are sufficiently below the flooding limit, close to but not at the flooding limit. Yeah, that back off is needed here. Similarly, a back off is needed here. Yeah. In the previous structure, by allowing the TPM to move, I basically avoided a back off in everything. Yeah. So I would go. My vote goes to what we did, which I rubbed off. Don't have it anymore. Yeah. You see, if you allow the TPM to move, then you are able to get tight control of everything. So I am not very rigid about no, the TPM has to be here. Sometimes operators are very rigid. You know, they will say, what the hell is this? When you are driving a car, speed is adjusted only by pressing the gas. But even there, when you have to brake, you step off this pedal and go to the next pedal, right? So that's, do you see what I am saying? Something similar here. Until the furnace is active, that is used as the TPM. Then until the boil up becomes active, that is used as the TPM. Then until the boil up in the deisobutanizer is active, that is used as the TPM. This allows you to have all three constraints active, no back off. Yes or no? Does that make sense? That's it. That is why I did what I did in that case. I think I thought through this and I always got stuck. Yeah, this will have to be given up, that will have to be given, there will be back off here, there will be back off there. I don't want that back off, so let me do it the other way. I think I did go through this thought process, but just didn't remember it. Okay. It may be that a back off here doesn't really make a big economic impact. The back off can be 10% and the increase in production or the loss in production because of that 10% back off is only 0.1%. Then you may say, yeah, theek hai, this is simpler, this is more conventional, let's do it this way. Okay. At least in this case, it turns out that a back off in this chap, in the furnace, actually gives you 3 to 4 or 5% throughput loss. That's a heck of a lot summed over a year of operation. Okay. Had it been that it only gives me a loss of about 0.1% if I have a 10% back off, then this would have been perfectly okay. Okay. The problem is it gives me significant loss in production. Yeah, therefore I did what I did. Okay. In fact, from the process I can clearly see that if this becomes active, it's not really a big deal, because anyway this stream is a small stream. Even if 5% NC4 goes to 10% NC4, that won't be a heck of a lot, because this is anyway 2 moles an hour or 2 kilomoles an hour. 5% of that is point, how much? 5% of 2 is how much? 0.1? 0.1 kilomoles an hour. Even if 0.1 goes to 0.2, right, it doesn't really make a big difference when the feed is 100. Yeah. So I may even be willing to live with this. I may even be willing to this is not going to, but I am not willing to live with the back off that's going to come up here. If maximum allowed temperature is 200 degrees Celsius, I will be operating at maybe 195 degrees Celsius. No, I'm sorry. Yeah, it's actually the same thing. If maximum furnace duty is X, I will be operating at 0.95 of X or maybe 0.9 of X, and that causes my throughput to be less by about 4-5%. That is something that's not acceptable to me. Do you see what I am saying? Which is why we did what we did. So, if the economic penalty is something that you are willing to live with, okay, let us say the economic penalty here would have been very small, then this is just fine, it's okay, it'll no big deal. It turns out, at least for this example, the economic penalty for this is the most, and economic penalty for back off in the boil ups of the 2 columns is not too much. That's how it turns out for this example, and that actually makes sense. By allowing more or less to leak out, this stream is small, it won't really make a big difference. Having back off here, what will it do? It will essentially limit your ability to, if the amount of NC4 that was recirculating around was, you could have put it down to 1%, now you are putting it down to 1.5%. Yeah. So economic penalty for back off from boil ups is not that much. Economic penalty for back off from furnace duty is quite severe. Therefore, we did what we did. Okay. Yes, you have a question.
Yeah. So here in the furnace part, we are considering the temperature of the reactor as constant, and hence you are saying that the Q furnace would be oscillating or whatever, it won't be constant.
Yeah.
Sir, I mean, what if we hold this furnace duty as constant and allow the temperature to vary? I mean, is that allowed or is that possible?
Well, your catalyst will get screwed. See, catalyst is expensive, and you would like to hold the temperature of the bed. You don't want the, see what happens is, if you have thermal swings, things melt and condense locally, and then your active sites which were exposed, which were active in that melting and solidification, what was previously exposed essentially becomes solid, and slowly but surely your catalyst starts losing activity. Even if you hold it constant, there will be some swings. So therefore what you have is typically a process, you know, you will run it for 2 years and then you will say, look, we need to change the catalyst because blah blah blah, right? That's what happens. Or we need to regenerate the catalyst. Thermal swings on catalysts are not desirable. So you do want to hold the temperature fixed. Okay, you say, okay, let it float. Yeah, you can let it float. Well, so let it float. Yeah, that's true. Actually, in this process, it can be done, as long as you are comfortable with the fact that the catalyst is not going to get screwed. In this process, you can let the temperature float. It will be very high, and then slowly, as you are jacking up the throughput, it will go down, 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 down. Yeah, that's possible. But that is something that an operator, in my opinion, would never agree, and the reason has to do with the health of the catalyst. any process is driven by the catalyst, the health of the catalyst is prime importance, and then you are saying, okay, let the temperature be whatever the hell it is, I don't care. So you may make more money over 6 months, but I guarantee you what if you are not controlling the temperature and if you are allowing large thermal swings, then the rate of degradation or deactivation of the catalyst will be much higher. Where you needed to shut down the process and change the catalyst every 2 years, with that kind of a scheme you may have to do it every 1 year, and then it's a different ball game altogether, you know. So I was able to get 5% extra production because I allowed the temperature to float, right? However, I have to take a shutdown, and then for my process to come back up, I lose actually more than 5% production. You see what I am saying? So basically what that means is that temperature has to be controlled. You can't let it float. But let us say it's a non-catalytic reaction. Let's say it's a thermal cracking kind of reaction. Even there you will have to control the temperature, because things may not crack or may over crack, right? If the temperature is too high, over cracking. If the temperature is too low, no cracking. So you really can't let it float.
There it will also be, there's a chance of runaway.
This is adiabatic, so there is no chance of runaway. It's adiabatic system, means the heat of reaction is not too much. Runaway is not the problem. Catalyst health is the problem here. Okay, so reactor letting the temperature float, maybe it's okay, but you better think n number of times before saying that it's okay. More likely you are missing something. Okay, in a simulation no problem, because in a simulation you never say that the catalyst activity is fixed, rate constant is fixed, activation energy is fixed, everything is fixed. But in real life those things are changing slowly but surely. And that is what is dictating, you know, you need to take a shutdown, new catalyst, etc., etc. Okay, so I would not let the temperature float. Okay, done.